Welcome, everybody, to today's Ascendo Reliability webinar. This is Fred Schenkelberg. And today I'm kind of digging way back into random topics that I've written about in the past and thought about in one way or the other, and ran across system effectiveness and said, I haven't talked about that a whole lot. Let's take a look at it. And so that's the topic for today. And more so, though, it's really about trade-offs, and we'll get into that as we get through this. Now, most of our products that we deal with and work with and so on are designed in some sort of fashion. They might be crafted on the fly, or they might be a rapid prototype. Usually some thought goes into was, what is it supposed to do? And is that adequate for what people expect it to do? And there's a piece of that process that goes into that. And as any of you knows, the design process is fraught with complexities. Um, I remember at one point there was people finally threw up their arms and said, well, it's DFX and it's designed for everything, fill in the blank. And I remember one engineer I was working with was like, you're here to talk about design for manufacturing and design for reliability. There's another team over there that's doing design for recyclability. There's another team doing for the environment. There's another team doing it for assembly. There's another team. He says, I got all these people telling me how to do the design, but none of them actually do the design. Um, but I digress. The design process in and of itself can be incredibly complex with lots of considerations and trade-offs. And the intent, though, is to create a product that, or a system that does what it's supposed to do and meet the needs. And I'll use a couple of different examples as we go on. And that it works. When it's called for, it's ready to go. And so I'm using this flashlight as an example here, is that when you need a flashlight, one, you can find it. That's kind of tricky sometimes, unless you anticipate a power outage or the need to get up when it's dark or walk around when it's dark. But you can find the button. On this particular image, the button has a recess around it so that, one, it won't accidentally turn on if it's just laid down the wrong way. But you can find it and push the button and it turns on. Now it's available. It's ready to go. It's got batteries. It's the element is viable. It'll take power and create light. All the other pieces are working, and it means it's ready to go. So that's one aspect of a product, is that when I need it, it works. If I load the dishwasher and push the button for it to wash the dishes, it actually starts, which is a good thing. And it's one of the considerations for the system effectiveness. And I'll get into more definitions of this. And then the third one is what ties us into it as reliability professional, is that it works long enough. And there's a lot of debate about what that actually means, at least in the literature that I've been looking through. And the hard part goes back to one of those real dilemmas that we have in reliability engineering, is you can measure the cost of a new design, the bill of materials cost, and the cost of manufacturing, the cost of advertising. A lot of that stuff can be budgeted out and monitored and measured every day. The design it's either ready or it's not. And it's kind of binary, and we can get a pretty decent estimate as we go through the design process. Are we able to ship on time? What's the risk to launching the product? The hard part is this last part is, well, will it last long enough? So that dishwasher I mentioned earlier, if I want it to last in my kitchen for at least 10 years, I'm quite sure that the folks that make these things don't test them for 10 years to see if it works. I'm quite sure they do a lot of other things to make sure it works, which then means it's an estimate, and sometimes a little more than a guess. And I know some people in this industry, in the industry of white appliances, and they do a great deal of things to make sure that it lasts as long as they expect customers to, as they understand customers expect it to last. And that's the part that's reliability. And the hard part of it is it's often difficult to measure, or it's not obvious how to measure it. And that keeps us employed as reliability professionals. But those are just three trade-offs. Does it do what is it meet the customer's expectation for the functions that it's supposed to have? Does it have the right functions for the way it's going to be used? Is it available? Is it turn on when you need it to turn on? And how do you go about doing that? And what's the variations of that? How often is it in maintenance, for example, or under repair, or needs servicing, or whatever that takes it out of service? And how often, how long does it last? Now, those three different things, and they obviously have trade-offs in them. And there's a handful of other measures or triangles or considerations, obviously, in the designing of a product. But system effectiveness really goes after these three things. And it's how do you optimize all three of these at once? And that's the part that I find the most interesting about system effectiveness. It makes you think about not what can you do, but what you should do. And I think that's a subtle way, or a short way of saying something that's actually a key concept that we all should consider as we're working on products and designs and creating systems and so on. All right, let me go back and do a little bit of background. So when I went looking for what do I know about system effectiveness, and where did it come from and all that kind of stuff, there's a handbook of reliability engineering. It was published in 1964, and it was either the Secretary of the Navy or somebody in the Department of the Navy, or the Navy branch of the military. Somebody high up signed off on this document that included this concept of system effectiveness. And they basically said there's three parts. Is it capable to do what it's supposed to do? Is it efficient, or does it have the right set of functions and performance characteristics that it does what we expect it to do? And so let's think of it as a car. Years and years ago, had a young family, and we needed something that was easy to get, small children in and out of their car seats on. So we went shopping for a minivan, and with this big sliding doors, so that you had really great access on both sides of the car to the second and third row. And so it was a feature that made our lives a little bit easier. And it had the range that we needed. It was in the price point that we could deal with. And it had, all the other performance features that we're interested in. Now, obviously, I wasn't looking for a sports car, because the intent was, the capability was to be able to move the family around from one activity to the other, or go shopping and have room to put groceries and stuff like that. It wasn't for cruising along the coast with the top down. And so part of this performance element of it is that, did we get the specifications right? Did we get the functions right? And we'll talk some more about that, but that's really not about what you can do as much as the trade-off is, well, what should it do? Does the customer get what they need for their investment in your product or system? Now, the second part was operational reliability, and it's really the question of how long will this work long enough? Is it, once the mission starts, once we get in the car and it starts, for example, or the flashlight turns on, will it last the trip? can I get to the store and back? Can I get to the pediatrician and back? And does it have all the features that perform? So like the doors actually close when we're trying to close them, and latches. Um, does it perform adequately for the mission? It's common for a military operation, but also does it operate without failure for some duration in time? If I need to do full overhaul every time we come back to the driveway, well, that affects the availability. And so, and as many of you know, reliability and availability are related. But the tactical availability, is it available? Is it ready to go when it should be? Is it in the right place? Is it charged or got fuel or whatever? And, it, are the wheels all on it? Or like with the flashlight, does it have the batteries in it? Is it charged? Is it functional, which would be ready to go? And so part of it also is, well, how often in the tactical availability? Is this a daily kind of flight mission, that profile that we expect it to do, or is it twice a day? How in a factory, are we going to run for an entire week or 2 weeks? Will the equipment not break down, or not break down too much, such that we get the throughput that we expect from it? So part of it is especially with repairable systems, this availability part becomes much more important. If you make a system that has incredible reliability and requires no maintenance, then the tactical availability becomes mute. Yet it also includes things like, did we get to understand how often it needed to be used? And all of those other factors, and we'll dive some more into it. Now, there's other definitions of system effectiveness. Let's see, one of them I ran into was performance, reliability, availability. Another one I ran into is availability, dependability, and capability. And I'm quite sure there's other ones. And when I was looking into it a little bit, it was most of the references were from the 60s. And it's in the time frame in the late 50s, early 60s, when the US military was building large systems like aircraft carriers and nuclear submarines and large tactical or strategic aircraft of one form or another. And they were paying a lot of attention to what they learned during the Second World War, is that, yeah, you can build them fast, and yet we got to make them work. And so they started thinking about, if we make it just work from a reliability or availability point of view, well, what do we give up on performance, and vice versa? And so part of this system effectiveness was a system to judge different approaches to the solving the particular problem that this design or this development process was to approach. And I thought, okay, well, that's clever. You don't see it around very much anymore. Yet I think it does still have some really good concepts in it that we still need to consider. Now, one of the things that has replaced it over the years is life cycle costing, which again includes a bunch of trade-offs, but it was really set at the idea that, well, if it costs us way too much to repair it all the time, and it has very expensive replacement components or maintenance activities or so on, what can we do to reduce that so that the total cost of ownership is reduced? It might be a trade-off. It might cost us more to build it right away. And like with a flashlight, I want a flashlight that works when it's cold, especially when I'm up early and trying to go up a mountain. And it's very common practice for mountain climbing and in the high countries to start before dawn, especially in the Sierras, because then the afternoons is when you get thunderstorms and the bad weather tends to show up, or it gets really windy. So you start really early, and the flashlight is really an essential piece of gear. Well, if that light doesn't work when it's 10 below zero, uh, Celsius or Fahrenheit, either way, it's cold. Uh, it's not very useful at that point. So it may cost a little more to get a flashlight that will survive the environment. But what about the batteries? There's different styles of batteries and different systems of batteries that work better at one temperature versus another. It also has to have enough battery power to last the day or the night for whatever reason you're doing it. And so you can see that there's a whole slew of different trade-offs on where do we impose the cost. Is it in the design process and then its initial purchase? Is all the cost there? But if we have to replace it with very expensive customized batteries that are hard to find and hard to install and take special tools to do, well, that imposes a whole lot of cost on the person using that flashlight that we could have traded off by making it easier to use standard batteries that are quickly replaceable. It really depends on what is the right set of trade-offs as to where the cost is going. Now, some argue, and I tend to agree, is that life cycle costing is good in the long run of looking at the total impact of purchase. The issue comes in is that, well, if I'm not the one paying for it, I tend to discount it. If it's impacting our profit margin in an adverse way, let's shift that cost to somebody else, whether it's insurance or a maintenance plan or an extended warranty or to the user directly. If the functionality is good enough, they still will buy it and they'll pay for the maintenance and they'll pay for all the other parts of it, the cost of ownership. Some markets that works just fine. In other markets, it's a disaster. When it's looking just at cost, it tends to focus on profitability, on stores, on maintenance costs, all those kinds of things, which is one way of looking at it. But I think it mutes a handful of the other criteria, and it tends to mitigate or minimize the input from the end user. Does it have the right functions? Does it have more like the system effectiveness? Does this do what I need it to do in the circumstances I need it to perform? Does the light last long enough in that environment, for example? And is it easy to change batteries that are able to be stored in my backpack, for example? Lifecycle costing kind of misses some of those features. You can get deeper into it and find a whole bunch of cool stuff on it, but it's not always the easiest thing to keep in mind when you're only dealing with numbers, with dollars. Another one that I'm sure many of you have run into and have used at one point or another is OEE. And it's similar to system effectiveness in a way that it has availability. But there it starts to break down into more of what's a big concern within production. And if we're making widgets or making flashlights, for example, is the factory equipment available, ready to run on Monday morning when the first shift starts? So do we have power? Do we have the raw materials? Do we have everything's put together and in working order so we can start up the equipment and start producing our flashlights? And then it's that equipment, that production line was probably designed to say, I'm going to use round number here, is let's say it was going to make 1,000 flashlights per hour. Well, we have breaks, we've got stoppages for jams, we got to wait for that forklift to bring the next pallet of material over here. That's all part of that system, that production system. And so instead of producing that 1,000 per hour that we wanted to, and let's say we only produced 80 per hour. Now that becomes a ratio of 80%, 0.8. And let's say availability, how often was it down? How often was equipment needing to be maintained and it was offline for the entire hour? And then we look at the time. When was it supposed to be available? What was its schedule? Say 8 hours. But let's say, oh, we have to do lunch and we really don't want to run the equipment without operator supervision and all kinds of reasons. So it's down for half an hour. So we get 7.5 hours. Now, you could argue that our schedule is for 7.5 hours, but let's take that half hour out for a maintenance, an unexpected breakdown, or accumulation of jams and so on. So it gets related to the efficiency, but the efficiency is measuring at the end of the day, did we make 1,000 or did we make something less than that? What was it able to do and what did we actually do? Now, maintenance downtime affects that. So I argue that sometimes these things are a little bit muddled, are related to each other, but they go after different kinds of measurement. So availability is really a maintenance measure. Is can you fix it fast and get it up, which has its own downsides. We've talked about that in the show or in this series on occasion. But the idea is that we measure the ratio of up versus downtime, the efficiency of what it made, and acceptable, which is not in system effectiveness, is did we make good parts? Were they consistent? So if I pick up one flashlight versus another one, do I get the same power output? Do I get the same light intensity? Is it easy to turn on and off? Is it as easy to replace the components or the batteries and so on? But at the end of the line, we're going to say, is this a good product or not? And what's the ratio? Now, if we make 1,000 units per hour, but 50% of them are scratched or dinged or non-functional or whatever, yeah, we got great plant efficiency, but we're making scrap. And so it was a trade-off, or a part of that trade-off of these three things is to balance out that, yeah, you can run really fast and ignore maintenance and shift it off to another time. Yet if you're making unacceptable products, then what's the point? And so equipment effectiveness briefly is similar to system effectiveness in that there's trade-offs. Now we can push the availability, reliability of our system so we don't have as many breakdowns or problems with it. We can make sure that we get equipment that's well balanced and the efficiency is got for critical steps has got redundancy and so on. Yet all of those come with trade-offs with one or more of these other things, and also with cost, which isn't necessarily overall counted in the system effectiveness or this equipment effectiveness concept. And there's others. There's other variations of this. I know in the design processes, do you want it designed fast, a quick turnaround on the design, or short time to market, or do you want it cheap, have the lowest possible cost, highest profit margin, or do you want it to work? It's quality and or reliability. Do you want it to be durable, for example? That inherently provides a set of trade-offs, and every organization faces these sets like this in different ways and sets priorities either through cultural norms and this is the way we do things, or explicitly in their project management. System effectiveness is just one of many of these types of systems to consider the trade-offs that we need to keep in mind as we go about doing our business. So here's a rhetorical question: is really, at the end of the day, on a day-to-day basis, and as we go through the design process, manufacturing process, and all the other parts and bits that we do to either create products in one form or another, is we have to make decisions. And these concepts of these, triad trade-off systems is a way to help us keep in mind, remind us, have a touchstone that says, well, what is important here? What are the things that we need to optimize? What do we need to keep stable? And what can we let, fall to the wayside, for example? And we'll talk about some more of these trade-offs and how it helps us make decisions in a little bit, in a few minutes here. But I want you to keep in mind is that these measures, these system effectiveness measure or life cycle costing measures and so on, are merely tools for us to help us understand, should I turn left here or should I turn right? Should I add a feature that's really expensive and difficult to maintain or not, for example? So it's a way for decisions to be guided, is probably the right way to say that. So let's get into it a little bit more. And I think I've talked about some of these, and some of them are really actually pretty straightforward. The capability, the performance capability is, does it do what it's supposed to do? If I take out a flashlight and I'm going for a walk down a trail, say at a campground, and I'm heading down to the store or the bathroom or whatever, while I don't necessarily need it to light up the entire sky and wake up everybody within the county or in the region, it should light up the road so I don't have inadvertently stumble over some obstacles or miss a fence line or something like that. There's a wide range of light intensity that's necessary in order for it to do what I needed it to do when I'm at this campground, for example. And the idea is that that's part of the design process and setting this functionality and those requirements document type stuff, engineering requirements documents, is our attempt to understand what the use case is, what the customer wants, what is their intended functionality portfolio that they need. Now, the hard part with a flashlight is that, let's say it's foggy and your beam of light gets obscured within a foot or two. How do we deal with that? Well, there are types of flashlights and light that has more penetrating power, but when it's a clear night, it's not necessarily all that useful. It blinds everybody that's around it, for example. And so it's anticipating the variability of the use, and then how do you optimize and trade off all the variables so that you get a light that, or a flashlight, for example, that's adequate. Now, some will have specialty ones. There'll be a headband attached to it, or it's LED with really long life, battery life on it, or it's super intensity, but it rips through the batteries pretty quick, for specialty applications. And it's defining your market. Well, it's not defining your market, it's understanding your market and getting that right. That's what performance capability is about. And think of it as like the vehicle. The minivan was good for a small family with young children, easy access, storage. We can haul soccer equipment in the back to soccer practice, stuff like that. Whereas if a sports car is not designed to have that capability, it doesn't even have a second row of seats, at least the sports car that I was looking at versus looking at minivans prior to us having small children. But the idea is that this is a part of the consideration, especially when you're setting out what it is you're going to go make. What is it supposed to do, not from an engineering point of view, but from a customer's point of view? And if I'm going to buy a piece of equipment for a factory, I have some specific things as the factory manager or the designer of that factory that I need it to do. And pulling something out of a catalog oftentimes isn't going to cut it. And so we often have custom built equipment or and so on to do that, or we build it ourselves. Sometimes, like in electronic manufacturing, the pick and place equipment that places components on boards that go into soldering, tend to be what's available. They're very efficient. They're easy to maintain, all of those good things. So some markets really pay attention to what the customer needs and helps them, whereas others, you get what you get and deal with it, kind of thing. And performance capability is obviously a trade-off and fraught with how do we interpret what people actually want. The reliability part, and I mentioned earlier, it's the one that's often fraught with, well, how do we measure this? So a battery in a flashlight, or the filament in the flashlight, or the LED as the element that creates the light, we have all kinds of different ways to measure those things, and some take longer than others. Some we can accelerate. What we don't do a good job of is accelerating it at very cold temperatures, at very high altitude, or along the ocean coast. And how long will this flashlight last when it's regularly exposed to salt and salt fog and high humidity, for example? What we need to do with operational reliability is not just how long will it last technically on the bench or in our lab, but how long will it last in the range of applications where it's actually going to be used? And that's a question we often don't pursue all that well. And so understanding the range of variability, the sets of stresses that affect your product, and the expectations of the customer is, if they know that we're going to be in this tunnel or this cave exploring it for 8 hours, I might want to take a backup battery set or two, and trade off the weight in what I'm carrying in order to make sure that I have light. I can't imagine the old cave explorers with candles, but they would take an extra candle and a way to light those candles, even in a damp or wet environment. The idea is that the reliability part is, and it always is, independent of this measure within effectiveness, is it's in the customer's perception. Did it last long enough? The closer we get to doing that, the better this measure will be in that system effectiveness measure or metric. Availability. Now, let's imagine, and I think this will get ahead of myself a little bit. Well, let's imagine that we have a really good flashlight and we're off lighting up the sky and our paths and all the other stuff up in the mountains. And the battery only lasts 20 minutes. And to replace the battery takes 20 minutes. I would go shopping upon the return of that trip. I probably would not be a happy hiker at that point. So the availability is, in some cases, repairability. It's also just that factor of reliability. If the battery I have lasts for the entire week of my trip and I don't have to replace it, that's great. I can do the maintenance when I'm back home and charge or replace the battery. On the other hand, if I have to take 6 battery packs with me and special tools and a jig to hold it in place so I could get the cover off and everything else, I'm not meeting that availability expectation. It's just not going to be available. But the other part is that, if that device is hard to find, it's kind of got a funky switch on it that sometimes works, sometimes doesn't. If I have to, I have one of these devices I'm looking at right now. It's used to turn on some lights, and it's a wireless device, but you have to hit the button about 8 times. Sometimes hold it closer. We think that works, but it's not terribly available. If I need the light on right now, I'll go do some other way to do it, because using that switch is pretty flaky. Now, I don't know exactly what the trade-offs were in the design of that thing, but it's really cool because it doesn't have a battery in it. Although sometimes you have to click it a bunch of times to get enough charge for it to actually work. I guess that's the trade-off. But the availability, does it work when it's supposed to? But also is, how often is it even available? So if you come out to your car and your son's got the tires off because he's practicing changing tires or rotating the tires for you, and you need to get to work, well, that's not available, is it? And so you can't even turn it on, where you could, I guess, but you're not going anywhere. So a couple different concepts within this availability piece. Some overlap with reliability. They're obviously related. At the end of the day, though, is that if you walk out to the driveway, is your car ready to go? If you find your flashlight in your pack and you turn it on, does it turn on? It's really the gist of this availability piece. So I haven't hit the chat all that often. Let me ask you this one. So system effectiveness has those three things, right? Capability, reliability, and availability. What is the gist of this thing? What is it really after? It's a short summary for this. See, Carl's got all kinds of links for life cycle cost analysis and a link to that handbook I mentioned early on. That's cool. Yeah, Kenneth, customer satisfaction. Um, the hard part is that we've tried for decades to be able to put that into a contract, and I'm thinking of the military systems, and yet I have no idea. I've never been involved with creating a government contract to create a product or a system. Um, I've usually gotten involved way after the fact, and the reliability aspects of a product are so constrained, or the availability aspects of it are so tied into knots, that there's really not a whole lot anybody can do about it. Some of the worst contracts I've ever seen were these weapons manufacturers working with the military, and I have no idea how that got so bad. But I don't know if that's just a U.S. military system. I haven't worked with foreign militaries and their procurement systems, but I suspect it is. Yeah, I think Kenneth and Michael are kind of in the gist of this thing, is that it's a set of criteria that we need to consider to keep the end user or the customer or the who's buying this thing or using whatever we're creating, that they get their investment back. They get satisfaction for their product. It does what it's supposed to do, and it does it to meet or exceed their expectations. Now, that's not a new concept by any means, and it's not the only way to focus on meeting the customer's expectations. Yet, what I find when I read through the definitions of the system effectiveness and all the variations of it, is it's a reminder for that development team and the design team to think about the customer, think about the person using this stuff, and make the trade-offs with them in mind. Diana Dini recently introduced me to this idea of actually hiring some of your primary customers or representatives of your customers and put them on the design team. Their role is to be the customer and to input design options and trade-offs and considerations from their point of view as a person going to use this product. One of the gists of the discussion is that it's the ability to use system effectiveness is a trade-off. It enables us to make trade-offs in light of considering what the customer needs and what their expectations are. Now, in some organizations, and some of you may be in these organizations, it's really feature set first, and we want to have the latest, greatest feature sets and technologies and so on. So we're pushing AI, we're pushing autonomous vehicles, we're pushing the edge of what's possible from a technical point of view. Now, some of those really cool new technologies are absolutely wonderful, except they don't work very long, or they're very difficult to work, where there's no repair systems and feature sets to keep it running and operating and so on. It's not proven technology because by definition, it's brand new and really cutting the edge of what we know how to do and manufacture. Now, over time, lot of that kinds of work goes on to find a combination of what is useful in the market, what do people want it to do, and that technology is a good solution for it. But then also it's a trade-off to, can we do it consistently? Does it last long enough, and so on? Does it meet the other criteria of availability and reliability and quality and cost and all of the other ones? So some organizations really do focus on, let's get the features, let's get the tech as cutting edge as we can, and let's see if we can upset a different market. Electric vehicles were, I think the first ones were way back in the early 1900s, great big lead acid batteries that were used in these systems. And it was actually an electric drive that let these vehicles go. It didn't catch on at that point for one reason or another. And more recently, it's being adopted for all kinds of different reasons. And it's still slowly being adopted. It's not the only option. I think here in California, it's going to be the only option within the decade, I think, by law. So I'm not terribly excited by that, but I'm looking forward to that. All the people that buy these systems today go work out all the bugs and kinks of it so that by the time I get around to getting one, it just works. But that's the difference of it. Now, let's say I wanted to make a flashlight that had amazing light intensity, and it had all kinds of features where I could change the beam width, I could change the color of it, I could set up for flashing as a beacon, I could set up ultraviolet and other ranges of frequencies of light, and for all kind infrared or all kinds of different things for whatever unknown reason. It would be a technical marvel to all be in a small handheld or something you could strap to your forehead and go outside with. And works underwater, works in high altitude, works in space, it just does everything. It has every feature you could ever want from a flashlight. Now, we're all pretty much reliability minded people on these attending this kind of webinar, and we know intuitively it's going to be a disaster. If I have this super intense light being emitted out of it, that takes power. And if I only have a square millimeter of battery power or space available, even with the most efficient batteries we can get out there, it won't last long, right? Or if something goes wrong, and now that we have 28 different sets of features on this thing, it's got a lot more ways it could go wrong rather than just shining light through an LED. So we suspect that it's a trade-off to the reliability and availability one. What I see people do is they'll focus on the feature set and really try to push the cutting edge, but they need to create floors or minimal acceptable criteria for reliability and availability. And Carl, you're exactly right. It's a natural part of the competition. Yet some organizations don't make that clear. Some say, engineers, we hire good engineers and you go figure it out. Now, if one engineer is really, really wants a good product that lasts a long time, they're not going to be too excited about adding a bunch of new features. But if the marketing department is saying, and the CEO, the founder is saying, oh, it's got to be leading edge, it's got to have all these features, that's our differentiator, there's a conflict. Now, if that's unstated, if it's not in the project management process, or it's not a clear part of the culture of what's the priorities and where's the trade-offs, where's the minimum acceptable barriers or guidelines for this thing, we can spend a lot of time creating a product that just isn't going to work and not meet anybody's needs. So part of the process of system effectiveness or life cycle costing or any of these other ones is to make it very clear, both in the way we do things, in the culture, and in our documents and statements and priorities of what's a trade-off and what's gone too far. We can't trade off all of the reliability or the quality of a product to get another feature in it. But where's the boundary? Where's the barrier? And so that's one of them that I've seen with, especially with tech forward type companies. The other one is reliability. We can make a flashlight that you'll never need to change the battery. We could. It won't have a whole hell of a lot of light, and you might not even have a switch because turning it on and off causes damage. It may weigh 300-400 pounds, not being very portable by normal human beings, at least not being. And it may be, the most reliable system you could ever make, yet nobody's going to buy it. It's not really acceptable for the functional sets of use cases and things like that. And so we have to moderate, well, how reliable is reliable enough? Is it to last one camping trip? Is it to last a month? Is it to have a long storage life like the flashlights in my house? We occasionally have power outages, or is there need to go, into the crawl space and we need a light there, and flashlights are the way to go. But we don't use it every day. I don't know if the batteries are fading or if it's got corrosion damage to it or whatever until I try to use it. And then I find out whether it's available or not. And if it does go, does the battery have enough charge to last the 20 minutes I need for that particular project? I don't really know until I get on with it. If I make a totally reliable system, it generally has other costs that impact its ability to do its primary function. I'm using a flashlight as an easy target to make these trade-offs. And it may be so expensive that very, very few people would buy it unless having a very long reliability or absolute perfect reliability, or as close as you can get to it for the mission time. If you're willing to pay for it, then there's a product there for you. Yet I don't see all that many organizations that do that. They usually set some criteria or set of metrics or targets for reliability based on market expectations or customers' expectations or requirements and contracts and things like that. And then making it way better than that might be a market advantage, or it might be a wasted effort that we really don't care. We'll change the battery every year in my smoke detector, whether it needs it or not. It's a low cost, easy thing to do. Hopefully all of you are doing that. But the idea is that what's the expectations? What's the customer's point of view on this for what they're going to use your product for? And then finally, the availability side of it. And it's obviously trade-off. If I can create a product that's very, very reliable, it has all the disadvantages of that last trade-off, all just perfect reliability, but nobody will buy it because it's too expensive or too heavy or too whatever. Availability in this regard goes to, well, if it's going to take me an hour and a half with special tools to replace the battery, it's offline for that hour and a half. Now, if that happens to be when I actually need the battery or need the flashlight, that's not available, right? If it's a system that says, oh, hey, you got to replace the battery, and I can schedule it, preventative maintenance type thing, that'd be great. We'll spend that hour and a half if I care to and have it ready to go so it's back to being in service and available for the next time it's used. The idea, though, is that I can make a waterproof flashlight, yet if I have to disassemble it and melt the potting material that's causing the water resistance elements of it or water tightness of it, because we know that seals won't last, or these other ways of making something airtight won't last, or if I put it in an hermetically sealed container, a can. And in order to replace the battery, you have to use a grinder to cut open access to it and then weld back on a lid. Well, the maintainability part of that goes out the window, basically, for somebody that's trying to carry a flashlight into a moist or damp environment, say a cave. There's always trade-offs. And in some cases, when it's critical like that, you just carry a redundant flashlight so that if this one gets wet or the batteries fail and we don't have replacement systems or tools for it, we pull out another one. The idea, though, is the availability part is part of the design, is how are we trading off? It's the serviceability, the maintainability, all those aspects to it, so that it will be available and not in service or not taking an inordinate amount of time to be put back into service. So if you push each one of these, and this is something I learned a long time ago, is when you have trade-offs like this, push each of the options to its extreme and see what happens. Think through the impacts on the other trade-offs and on the customer satisfaction in this case. Where's the boundary, though? And that's the hard part in these trade-offs and these measures like this, is that you and I and everybody else will come up with different boundaries. Is what's an acceptable time to replace the battery? And do we do it with conventions so that a person puts in one AA, positive in, and the X one next to it is positive out? Or we're going to be clever and set up that battery box so they both go in the same way. And it doesn't matter which way you put it in, as long as they're both the same way, they work. Now, that's not conventional. And if you don't have a light, you might not see the indicators of which way they're supposed to go. So that's a design trade-off in affecting the availability of your system. If you have to go through all the permutations of, positive in, positive out for 2 or 3 batteries, you might be there a while. If you use it in the conventional way, one in, one out, it might go pretty quick. That might be the first one most people would try. But you can see how that's a decision that organization needs to make. And it affects the potential availability to their system. All right. So I got a couple minutes left here. There's more stuff. Let's see. I think I'm all caught up on that. Oh, no, there's more here. Lots of ways to do trade-off analysis. They're definitely right. But getting a customer involved is a way. Doing focus groups is a conventional way. Totally ignore them, and it seems to be the most common. But how do you guys do this? And does anybody use system effectiveness? I'm very curious, because I know that it's an older concept, and I've heard from multiple sources, and in my research, it doesn't seem to be prevalent these days. There's not much being talked about or read about or written about, I should say. Yet I think that concept of trade-offs and setting boundaries so that it guides your decisions across your organization in a consistent manner is the gist of thinking through and documenting what is your system effectiveness guidelines and boundaries, or life cycle costing, or equipment efficiencies, or so on. What is it you're really trying to measure, and where are the trade-offs? Because with any of these measures and metrics, there's always ways to game it to maximize one thing or another, or the overall measure. At the end of the day, what's the goal? How are you actually using these things? And I'm really starting to question using the system I'm using to do the webinars, because today we had 2 crashes on it. One about 5 minutes before the start, another one about 34 minutes into it. So it's back into more deep trade-offs in considerations for this. Do I try a different system? And of course, it's the 3 different major vendors involved are all saying, well, it's somebody else's fault. So I really don't know. Time to make some phone calls, I guess. All right. Oh, the audio crashed before the video. Interesting. Thanks, Michael. Another bit of info I can bring to the table. All right. Anything else? We've got a couple minutes here. I have really no idea what I'm going to talk about next month. As I usually do, I don't look ahead. I know I've got a plan, but I don't know where it's at. Yeah, Larry, there's lots, and one of the things I'm working on, and I saw a reference to a concept called hierarchy of, what was it called? It wasn't hierarchy of insights. And it was a Seth Godin blog. And he said, the hierarchy, according to Ackoff years ago, was that we have data, we have information that comes from the data, we have, I'm drawing a blank on it. There's 5 parts of it. Data, information, knowledge, and then wisdom. And there's one other one in there I'm missing. And he said, we spend a whole lot of time measuring data, collecting data, storing data, arguing over data, and very little about the wisdom. That's the last one, is the wisdom part, which is at the other end of the hierarchy. Is data, information, something, knowledge, wisdom. And so I'm thinking about writing a article series on that hierarchy. And the data part is important. It's the foundation for a lot of these things. Yet, are we spending enough time on how we interpret it, how we understand? That's the other one, is knowledge, information, understanding, knowledge, and wisdom. Do we spend enough time understanding it? And I think, Larry, you've run into it too, is where people will put it in a calculator or a software package and create a plot or get a number out of it and say, all right, we're done. And not really understanding what it means or how to interpret it, or what is it, what were the trade-offs, what was the underlying assumptions that we made, those kinds of things that helps us to understand the information. And then what are we going to do with that? How does that stick with us to create knowledge and so on? So I'm looking forward to building on this idea of different data sets and different ways we go about analyzing data, but how do we actually make it something more systemically useful for us and for our organizations? So we'll see how that turns out. All right. Now, I have no idea if this thing was recording this last part, so it may be a truncated webinar at the end of the day, but I'm going to go ahead and stop the recording. Looks like it was working. And thank everybody for joining today.